Good evening, stargazers, and welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reid, and tonight we're embarking on a journey through mind-bending possibilities in theoretical physics. What if the universe's most feared objects, black holes, were actually cosmic doorways? What if these gravitational monsters that consume everything in their path are not cosmic dead ends, but rather gateways to distant realms of space and time? Tonight we'll explore the fascinating scientific theories that suggest black holes might serve as portals, connecting our universe to places beyond our wildest imagination. We'll journey through Einstein's revolutionary mathematics, discover the mysterious white holes that could serve as cosmic exits, and examine how quantum mechanics might make interdimensional travel theoretically possible. If you enjoy these types of videos that blend cutting-edge science with relaxing cosmic exploration, please give this video a thumbs up and consider subscribing for more nocturnal astronomical adventures. And leave a comment telling me which destination through a black hole portal you'd choose if you could travel anywhere in the cosmos. I'd love to hear your cosmic wanderlust. Alright, let's dive in. The story of black holes as portals begins in 1935 with two brilliant physicists whose names you might recognize, Albert Einstein and Nathan Rosen. These scientific pioneers were studying the strange mathematical equations that describe black holes and discovered something extraordinary hidden within the mathematics. Think of spacetime like a vast rubber sheet stretched tight. When a massive star collapses into a black hole, it creates such an intense gravitational field that it literally punches a hole through this cosmic fabric. Einstein and Rosen realized that the mathematics didn't just describe a hole, but potentially a tunnel that could connect two separate points in the universe. They called this theoretical passage an Einstein-Rosen bridge, though we know it today by a more familiar name, a wormhole. Einstein and Rosen proposed that a black hole could combine with a white hole to form a bridge between two areas of spacetime, where matter would be drawn into the black hole on one side of the bridge and then expelled through the white hole on the other side. Picture a cosmic subway system where black holes serve as the downtown stations, collecting passengers and cargo, while somewhere else in the universe, white holes act as the destination platforms, delivering everything that went in. The mathematics behind this idea emerged directly from Einstein's theory of general relativity, the same equations that have successfully predicted countless cosmic phenomena from the bending of light around massive stars to the precise timing of GPS satellites orbiting Earth. These aren't science fiction fantasies, but rather predictions that flow naturally from our most successful theory of gravity and spacetime. However, these early wormhole theories came with a significant caveat. According to theoretical analysis, the Einstein-Rosen bridge is quite unstable. Traditional wormholes would collapse faster than light could travel through them, making them cosmic mousetraps rather than functional gateways. Any unfortunate traveler attempting passage would be crushed by collapsing spacetime before completing the journey. But science rarely accepts defeat so easily. The instability problem sparked decades of research into how these cosmic tunnels might be stabilized, leading to discoveries about exotic matter, negative energy, and quantum mechanics that we'll explore in our upcoming segments. The profound implications of Einstein-Rosen bridges extend far beyond simple interstellar travel. If black holes truly function as portals, they could connect not just distant regions of our universe, but potentially entirely different universes, different timelines, or dimensions we can barely imagine. According to the Penrose diagram, an object traveling faster than light will cross the black hole and will emerge from another end into a different space, time, or universe, forming an interuniversal wormhole. To understand how black holes might function as portals, we must first meet their theoretical twins, white holes. Scientists like Roger Penrose theorize that a white hole is like an exit for a black hole in another universe, where material would fall into a black hole in one universe and would get ejected into another universe via a white hole. If black holes are cosmic vacuum cleaners, then white holes are cosmic geysers, fountains of matter and energy erupting into space. A white hole is a theoretical region of spacetime that is the opposite of a black hole. While a black hole is a region from which nothing, not even light, can escape, a white hole is a region from which nothing can enter. Imagine trying to pour water into a fire hydrant while it's shooting water out at full pressure. That's essentially what approaching a white hole would be like, except instead of water, it's spacetime itself pushing against you with incredible force. The mathematics that describe white holes come from the exact same equations as black holes, just with time running in reverse. These equations describe the curvature of spacetime due to massive objects. Whereas black holes are born from the collapse of stars, white holes represent the theoretical birth of space, time, and potentially even universes, theorized to exist based on the very same math and general relativity concepts as black holes. Think of this cosmic relationship like a massive hourglass lying on its side. Sand pours into the narrow neck on one side, representing matter falling into a black hole. On the other side, sand streams out of the opposite neck, representing matter erupting from a white hole. The narrow connecting passage between them forms the wormhole tunnel through spacetime. While black holes devour everything in their vicinity, white holes are theorized to do the opposite, pushing out matter and light into the cosmos, ejecting matter and light while never absorbing any. This creates a perfect cosmic recycling system where nothing is truly lost, merely transferred from one location to another through the fabric of spacetime itself. But here's where the mystery deepens. If white holes are mathematical necessities that should exist according to our understanding of physics, where are they? General relativity predicts their existence, but astronomers haven't found any yet. This absence presents one of modern astronomy's most intriguing puzzles. Some theoretical physicists propose that white holes might be incredibly short-lived, existing for only brief moments before becoming unstable and transforming into something else. Others suggest they might be camouflaged as other cosmic phenomena we already observe but don't recognize as white holes. Could some of the universe's most energetic events, like gamma-ray bursts or quasar emissions, actually be white holes expelling matter from distant black holes? There's another fascinating possibility that addresses both the stability problem and the missing white hole mystery. Some scientists theorize that the Big Bang itself might have been a white hole, the ultimate cosmic exit ramp where all the matter and energy of our universe came pouring through from somewhere else. White holes represent the theoretical birth of space, time, and potentially even universes. This concept transforms our entire cosmic origin story. Instead of our universe beginning from a singular point of infinite density, it might have been born from matter and energy streaming through a cosmic portal from an older, parent universe. Our cosmos becomes not the beginning of everything, but rather the continuation of an eternal cycle of matter and energy flowing between interconnected universes through black hole and white hole pairs. The white hole connection also provides a potential solution to one of black hole physics' greatest puzzles, the information paradox. If information falling into black holes gets destroyed, it violates fundamental principles of quantum mechanics. But if black holes are connected to white holes, then information isn't destroyed but rather transmitted through the wormhole tunnel, emerging intact in a different location. While Einstein's classical theory of relativity predicts wormholes, quantum mechanics adds layers of complexity and possibility to black hole portals that make the reality even stranger than the original theory. At the quantum level, reality operates by fundamentally different rules than our everyday experience. Particles can exist in multiple states simultaneously, appear to communicate instantaneously across vast distances, and tunnel through barriers that should be impenetrable. These quantum phenomena might provide the unusual mechanisms necessary to stabilize wormhole portals and make black hole travel possible. The key lies in something called negative energy density. Think of regular matter and energy as having positive weight on the cosmic scales of spacetime. Negative energy would be like negative weight, pushing spacetime outward rather than pulling it inward. Just as positive energy creates gravity and curves spacetime inward to form black holes, negative energy would curve spacetime outward, creating a repulsive effect that could hold the wormhole tunnel open against its natural tendency to collapse. But where would such unusual negative energy come from? Quantum mechanics provides several tantalizing possibilities. The vacuum of space isn't actually empty but seethes with quantum fluctuations, virtual particles constantly appearing and disappearing in pairs. Under certain conditions, these quantum effects can produce regions of negative energy density, creating what physicists call the Casimir effect. Imagine trying to keep a tunnel open in wet sand at the beach. Normally, the tunnel would collapse immediately. But if you could install supports that push the sand walls outward, the tunnel would remain stable. Negative energy would function as these supports for wormhole tunnels, creating a stable passage through the curved spacetime around black holes. The quantum mechanical properties of black holes themselves might contribute to portal stability. Black holes emit Hawking radiation, a quantum process where particle pairs created at the event horizon result in energy slowly radiating away from the black hole. This quantum mechanical process connects the black hole's interior to the external universe in ways that purely classical physics cannot describe. Some theories suggest that quantum entanglement, the mysterious connection between particles that allows them to influence each other instantaneously across any distance, might provide the backbone for wormhole structures. If particles falling into a black hole remain quantum entangled with particles outside, they could create quantum threads that span the wormhole tunnel, providing information pathways that maintain the connection between the black hole and its corresponding white hole exit. Recent advances in quantum computing have allowed scientists to simulate simplified wormhole behavior in laboratory settings. These quantum simulations demonstrate that information can indeed travel through wormhole-like connections, though the experimental wormholes exist only in the quantum realm rather than as macroscopic spacetime structures. The quantum approach to wormhole physics also addresses the grandfather paradox of time travel. If wormholes connect different points in time as well as space, traveling through them could theoretically allow someone to arrive in the past and alter events. Quantum mechanics suggests that such paradoxes might be resolved through quantum superposition, where multiple timeline possibilities exist simultaneously until observation collapses them into a single reality. Consider quantum tunneling, where particles routinely pass through energy barriers that classical physics says should be impenetrable. A particle approaching a barrier has a probability wave that extends beyond the obstacle. Sometimes, the particle materializes on the other side without ever having enough energy to climb over. This quantum phenomenon might provide a model for how matter and information could traverse the extreme gravitational barriers inside black holes. The quantum vacuum itself might serve as a medium for portal connections. Quantum field theory describes space as filled with zero-point energy, a seething foam of virtual particles and antiparticles constantly appearing and vanishing. In regions of extreme curvature like those near black holes, these quantum vacuum fluctuations could be amplified and organized into structures that support stable wormhole connections. Another quantum possibility involves the holographic principle, which suggests that all information contained within a volume of space can be encoded on its two-dimensional boundary. If black holes are holographic structures, then the information falling into them might be preserved on the event horizon surface and somehow transmitted through quantum channels to corresponding white hole boundaries in distant locations. The intersection of quantum mechanics and general relativity in black hole physics has led to one of the most ambitious theories in modern physics, string theory. In string theory's multidimensional framework, black holes might connect not just different regions of our three-dimensional space, but different dimensional branes floating in higher dimensional space. A black hole portal could literally transport matter and energy to universes with entirely different physical laws and dimensional structures. These quantum mechanical considerations transform black holes from simple gravitational objects into complex information processing systems that could serve as cosmic routers, directing matter, energy, and information between different destinations based on quantum mechanical rules we're only beginning to understand. The Einstein-Rosen bridges we've discussed so far have a fatal flaw for any would-be cosmic traveler. They collapse faster than light can cross them. But in 1988, physicists Kip Thorne and Michael Morris published groundbreaking research describing a different kind of wormhole, one that could remain stable and allow safe passage from one end to the other. The Thorne and Morris paper was titled Wormholes in Space-Time and Their Use for Interstellar Travel, a tool for teaching general relativity, and helped establish wormhole research as a new area of academic inquiry. These traversable wormholes require unusual matter with negative energy density to keep them open, but they offer the tantalizing possibility of practical interstellar and even interdimensional travel. Unlike the unstable Einstein-Rosen bridges, traversable wormholes would have no event horizon, meaning travelers could pass through them safely and even return to report their experiences. Think of the difference between trying to swim up a waterfall versus traveling through a well-engineered tunnel. The original Einstein-Rosen bridges are like attempting to swim backwards up Niagara Falls, while traversable wormholes are like driving through a carefully constructed highway tunnel with proper lighting, ventilation, and structural support. The engineering requirements for such cosmic tunnels are staggering. The unusual matter needed to stabilize a human traversable wormhole would need to have negative mass energy equivalent to the mass of Jupiter, distributed in a thin shell around the wormhole throat. This material would need to violate the dominant energy condition, possessing properties unlike any matter we've ever observed in nature. But here's where black holes might offer a natural solution to the unusual matter problem. Some theoretical models suggest that rotating black holes, called Kerr black holes, might already contain the space-time distortions necessary to support traversable wormhole connections. The rotation creates a complex structure called an ergosphere, where space-time itself is dragged around the black hole. Within this region, the normal relationship between matter, energy, and gravity becomes twisted in ways that might naturally produce the negative energy densities required for wormhole stability. The engineering challenges extend beyond unusual matter to navigation and communication. How would travelers know where their chosen black hole portal leads? Some theories propose that wormhole connections might be established by quantum entanglement between black holes that formed from originally connected matter. Twin stars that collapse into black holes might maintain quantum connections that translate into wormhole pathways, creating a cosmic network based on the universe's gravitational and quantum history. Advanced civilizations might even be able to engineer artificial wormhole networks. By carefully manipulating black hole formation, mergers, and rotation, cosmic engineers could potentially create transportation systems spanning entire galaxies. Such networks would require technology beyond our current capabilities, but the physics suggests they might be theoretically possible. Consider the energy requirements for wormhole creation and maintenance. The energy needed to artificially create a traversable wormhole might equal the total energy output of entire stars. However, naturally occurring black holes already contain enormous gravitational energy that might be harnessed and redirected to support portal functions. By adding carefully engineered unusual matter structures, existing black holes might be converted into functional gateways. The temporal aspects of wormhole travel add another layer of engineering complexity. If wormholes connect different points in time as well as space, travelers might emerge from black hole portals in the past or future of their destination. Advanced civilizations would need to develop sophisticated methods for temporal navigation, perhaps using quantum mechanical principles to target specific time coordinates. The implications of functional black hole portal networks extend far beyond transportation. They would enable instantaneous communication across cosmic distances, resource sharing between galactic civilizations, and scientific collaboration on scales currently unimaginable. An advanced civilization could distribute its population across multiple galaxies while maintaining cultural and technological unity through wormhole connections. Perhaps the most mind-expanding possibility of black hole portals involves their potential to connect not just distant regions of our universe, but entirely different universes altogether. According to the Penrose diagram, an object traveling faster than light will cross the black hole and will emerge from another end into a different space, time, or universe, creating an interuniversal wormhole that challenges our very understanding of reality itself. The mathematical framework of general relativity doesn't restrict wormhole connections to our single universe. The equations naturally extend to scenarios where space-time tunnels could breach the boundaries between parallel realities, each with potentially different physical laws, different histories, and different evolutionary paths. This transforms black holes from simple gravitational objects into cosmic lighthouses marking doorways between infinite alternate realities. Consider the profound implications of accessing parallel universes through black hole portals. In some alternate realities, different choices during critical moments in cosmic history might have led to universes where stars formed differently, where life evolved along completely different pathways, or where the fundamental constants of physics themselves take different values. A black hole portal network could provide access to a cosmic library containing every possible variation of reality. The many-worlds interpretation of quantum mechanics suggests that every quantum measurement creates branching realities where all possible outcomes occur simultaneously. In this framework, black holes might serve as natural connection points between these branching timelines. Matter falling into a black hole in our universe might emerge in alternate realities where quantum coin flips came up differently, where civilizations made different choices, where evolutionary history took alternate paths. String theory extends these possibilities even further by proposing that our universe is one of countless dimensional brains floating in higher dimensional space. Black holes might puncture through our three-dimensional brain to connect with entirely different dimensional structures. A portal traveler could emerge in universes with more or fewer spatial dimensions, where time flows differently, or where matter and energy behave according to completely unfamiliar rules. The navigation challenges for interdimensional portal travel become almost incomprehensibly complex. How would travelers choose which alternate reality to visit from among infinite possibilities? Some theories suggest that quantum entanglement or consciousness itself might serve as a targeting mechanism, with travelers naturally drawn toward realities that resonate with their quantum signatures or mental states. The concept of cosmic natural selection takes on new meaning in a multiverse connected by black hole portals. Universes that successfully create stable wormhole networks might have advantages in sharing resources, information, and even biological material with their alternate versions. This could lead to accelerated evolution and development across multiple realities simultaneously. Since the beginning of the universe, space-time has been expanding, and there is a possibility that primordial wormholes might also have gotten larger. These ancient portals, formed in the first moments after the Big Bang, could now serve as gateways between universes that have been evolving separately for billions of years. With the current knowledge, we cannot predict their size and nature, but they might be the key to understanding how our universe connects to the broader multiverse. The philosophical implications of interdimensional black hole portals challenge fundamental assumptions about identity, causality, and meaning. If infinite versions of ourselves exist in alternate realities accessible through black hole gateways, what makes any individual version special or unique? The answers might depend on quantum mechanical principles that preserve information across dimensional boundaries while allowing for infinite variation in how that information manifests. Advanced civilizations with access to interdimensional portal networks might develop entirely new forms of existence that span multiple realities simultaneously. They could maintain synchronized societies across parallel universes, share technological advances between alternate versions of themselves, and explore the full range of possible evolutionary and cultural developments. The energy signatures of interdimensional wormholes might be detectable through their effects on space-time geometry, gravitational wave patterns, or exotic particle emissions that don't match any known physics from our single universe. As we stand on the threshold of a new era in gravitational wave astronomy, space-based telescopes, and quantum computing, the search for evidence of black hole portals is transitioning from purely theoretical speculation to observational science. Detecting these as yet hypothetical objects could not only provide evidence of quantum gravity but also revolutionize our understanding of cosmic structure and our place in the broader multiverse. The recent detection of gravitational waves by observatories has opened entirely new windows into black hole physics. These ripples in spacetime carry information about black hole mergers, their internal structure, and the extreme physics occurring near their event horizons. Future gravitational wave detectors might be sensitive enough to detect the unique signatures of wormhole connections, such as the characteristic vibrations of exotic matter or the gravitational echoes of matter disappearing from one location and appearing elsewhere. Advanced space telescopes currently under development will possess unprecedented capabilities for observing the immediate environments around black holes. The Event Horizon Telescope has already provided direct images of black hole shadows, and next-generation instruments might be able to detect the subtle spacetime distortions that would indicate wormhole throat openings. These observations could reveal whether black holes are truly isolated objects or connected to distant cosmic regions through spacetime tunnels. The quantum information revolution is providing new tools for testing wormhole theories in laboratory settings. Quantum computers can simulate the complex entanglement patterns that theoretical wormholes would create, allowing scientists to explore portal physics using controllable quantum systems. These experiments might reveal fundamental principles about how information travels through wormhole connections and whether quantum entanglement can indeed serve as the backbone for spacetime tunnels. Theoretical advances in quantum gravity are beginning to bridge the gap between general relativity and quantum mechanics in ways that could make wormhole predictions more precise and testable. Loop quantum gravity, string theory, and other approaches to quantum gravity each make specific predictions about how black holes might connect to distant regions of spacetime. As these theories mature, They will generate increasingly detailed predictions that future observations can test. The implications of confirming black hole portals extend far beyond pure science into practical considerations for humanity's cosmic future. If black holes truly serve as gateways to distant regions of the universe or alternate realities, they represent the ultimate frontier for exploration and expansion. Civilizations that master portal technology could transcend the limitations of light speed travel and access resources distributed across cosmic scales. But portal technology would also raise profound questions about safety and regulation. How would we prevent potentially hostile entities from other universes from using portal networks to access our reality? What protocols would govern interdimensional travel and communication? The development of portal technology would require unprecedented international cooperation and careful consideration of cosmic-scale consequences. The search for extraterrestrial intelligence takes on new dimensions when we consider portal possibilities. Advanced alien civilizations might already be using black hole portal networks for communication and travel. The apparent absence of obvious alien visitors in our solar system might simply reflect the fact that sufficiently advanced civilizations use portal networks that bypass normal space entirely. We might need to look for portal signatures rather than conventional spacecraft to detect advanced cosmic civilizations. The long-term survival of intelligent life in the universe might depend on portal technology. As stars age and galaxies drift apart due to cosmic expansion, portal networks could provide ways for civilizations to access fresh energy sources and habitable locations across multiple universes. Black holes might serve as lifelines that allow consciousness and culture to persist far beyond the natural lifespan of any single universe. And on that note, whether black holes ultimately prove to be simple gravitational objects or gateways to infinite cosmic possibilities, they represent the frontier where our understanding of physics meets the deepest mysteries of existence. Thank you for joining me on this journey through the theoretical landscapes of portal physics and interdimensional possibilities. Until next time, keep looking up, and remember that the universe's greatest secrets might be hiding just beyond the event horizon of your nearest black hole.